Richard Bowles of University of Saskatchewan, Canada, and the title of the talk is Computative Nucleation in Nanoparticle Clusters.
A chance to come and tell you about some of the things we're doing in our group. With reference to nucleation, we're interested in a variety of nucleation phenomena, but in particular we're wanting to look at what happens when you deal with systems that have very small particles. And so one example of that is going to be the clusters, but we're also interested in things like heterogeneous nucleation, that's occurring on a nanometer heterogeneity, things like deliquescence, again when the particles are becoming very, very small. And when you get these very small particles, you get a whole host of new phenomena, which is quite a challenge. And the sort of things we're going to see in particular for nucleation in these nanoparticles, which consist of usually like several hundred up to 1,000 atoms, there are two main features. There's going to be a surface area. Obviously these particles are small, and so there's a new interface between the liquid droplet and the vapor phase that you don't have when you're crystallizing in the bulk. Obviously a crystallite that's forming an embryo that's forming in the solid phase or forming in the bulk phase is totally surrounded by the liquid phase. But in a nanoparticle we're going to see that this new interface is going to have an important effect. And that may influence the type of structures that are formed and certainly can influence the rate of nucleation. The other problem that comes about, that we'll see a lot of, is that there are multiple structures that have very similar free energies. And so the question becomes, which of these structures will actually form? And we're going to see that when you do a quench experiment where you drop the temperature of the liquid droplet and watch it freezes two different structures. And so you get a sort of competitive nucleation process, and really that's going to be the main topic. And so, as always, there's lots of people who do this work. And so Eduardo has done some work on gold. Ivan was a postdoc with me. He's now at the University of Memorial University. And I had an undergraduate, and I've got a new graduate student who's working on this. So they've done all the work, and so I want to acknowledge them right up the front. Okay, so what am I going to do? I'm going to give a bit of background to these problems, what type of structures we see, and how we should look at them. And sort of out of that will rise a few questions about what sort of things should we be looking for, and how do these things actually nucleate to form these different structures. I'll talk a little bit about simulation techniques. Obviously this is something you'll see a lot of, and they're pretty standard techniques, so I'll just briefly go over that. And then we've done some surface nucleation in gold nanoparticles, so that's one system we'll see. We've had a look at medium-sized Lennard-Jones nanoparticles, and then based on the work we did here, we've gone back and we've started to have a look at this gold material again in light of what we've learned here. And then I'll just have a brief summary of our general results and questions of directions we're going in the future. And the key thing here is this is very much a work in progress, as you'll see. Okay, so what is the question about different structures in clusters? So when we're talking about a bulk system of just sort of spherically symmetric potential, then generally the FCC type structure is going to be your most stable state. Okay? But when you get smaller and smaller systems, then different non-crystalline structures become important. And so what we have in particular, we're going to have main structures that we're going to see icosahedra. And there are actually different types of icosahedra with different surface reconstructions that will become important. We have decahedral structures, okay, and I'll define the symmetries and the atom types in a minute. And then we have our FCC. And so what we see if we look at the energy, so this is a kind of measure of the excess energy associated with a different size system. And so if we take the energy inside the bulk, or energy of the system, which is all of these atoms, we minus out the bulk coherence energy per particle, so this is what you'd see in the bulk, and we just divide by n to the 2/3, which is the surface term, what you get is this surface energy. And if you plot that as the size of the cluster, what you see for the different structures, an icosahedra, and here we have our decahedral structure coming through here, and then we have eventually our FCC structure. There are ranges of system sizes that each structure is the most stable state. And so the progression through here is sort of defined by the sort of stresses that we see in the system. So if we have a look at the details of what these structures look like, what we see is an icosahedra is actually, you can think of that as being built from a whole set of 20 tetrahedra, which are all packed together. And so those tetrahedra all meet at the center Okay, so that's the central point. And then they face pack together, and these are essentially the edges of the tetrahedra going into the center. And so we have 20 of these. So along these edges, the atoms are actually got five-fold symmetry. Inside each of these tetrahedra, the atoms have FCC-type symmetries. The planes where they meet at interfaces, the atoms actually have HCP symmetries. And so depending on where you look inside the structure, the local environment of any one atom is going to be very, very different. And so this brings about one of the big challenges that I think is that, not as just in this field, but in general questions of nucleation and growth, is how do complex structures that are very, very different with respect to, depending on what level you look at and where you look inside the system, how do they actually nucleate and how do they learn about their global structure? For example, if I'm just growing an FCC structure, I can get a small crystallite, and then all I need to do is I need to propagate that structure in all directions. But if I have something like an icosahedra, where the local structure of any one atom is very, very different depending on where I look, how do I get these atoms all together and arranged such that they grow to this global structure? So that's one of the big questions that we're hopefully sort of getting an answer to. The reason we see this progression is simply because these tetrahedra, while we have 20 of them, don't pack exceedingly well. There's actually stress associated with filling space with tetrahedra. To fill that space, you've got to stress the interfaces. That stress grows as the tetrahedra get bigger. And so here's just an example of trying to pack 5 tetrahedra together in space, and there's a gap. So you need to stress the system to get these to fill space. And so as the system grows, eventually that stress becomes too big, and so you change phase into the decahedral structure. I should just mention about the decahedral structure. That is different to this. Now what you've got is a line of five-fold symmetry atoms running through the center. And we'll see pictures of these in a minute. And you can kind of see on here that you've got 5 axes coming out of HCP packings, and then in between all of these you have the FCC. And then the FCC structure itself, all of these atoms are the same type of structure. So they're all local symmetries related to FCC structure. And so that's the sort of background to the general phase behavior. What happens when you freeze these guys? So Bartel started looking at this back in 2000, and what they did was just take a different size gold nanoparticles, heat them up, make sure they were melted, then just drop the temperature below the freezing. And they chose different size clusters, and they dropped them to different temperatures. And so then what they did was they just let the simulation progress in the molecular dynamics, and then at the end of that dynamics, have a look at what type of structures they had. And so, in particular for gold, the FCC structure becomes quite stable, at least theoretically. I don't know that this is true in experiments, but theoretically about 300 to 400 atoms, the FCC structure becomes the most stable. So even above those sizes, and considerably above those sizes, we see different structures being formed. In fact, we see all 3 sets of structures. And so the question becomes, what decides which of these structures are being formed? And it's a comparative process. It's sort of a probabilistic sense. You cool it down. You don't know exactly which structure you're going to get, but you get one of these. And the question we want to know is, what determines which one? The other problem that I mentioned that is important is the role of this surface. The fact that now with a nanoparticle compared to the bulk, you have a new interface. The fact that this guy is sitting here, and in principle they're surrounded by a vapor, because all these clusters obviously have a vapor pressure. In principle, the simulations are really done on isolated clusters, but this interface is present. And so what they see, if you cool down a gold nanoparticle and you start just identifying which are the solid-like particles, and I'll describe all those details later, you can see the surface atoms start to order, and then eventually they order some more as you continue to cool this down. Eventually you form something close to an ideal icosahedra. And so the idea here was that the fact that you had the surface nucleation occurring, or the surface ordering occurring, was driving it into this icosahedral structure. And we'll come back to that kind of idea later on, whether this is actually true or not. When you expect to see nucleation at the surface is if you take a phenomenological approach, is when you would expect partial wetting. So when the condition for partial wetting is met, for the liquid on its crystal, then you would expect this to be a lower free energy pathway compared to the bulk. Okay, so these are two sort of important features that we'll see as we go through. Why is surface important? So this isn't quite so related to the nanoparticles that we're interested in, at least for this talk, but the surface, whether nucleation of these nanoparticles occurs at the surface, is important atmospherically. So here we have, in fact, a set of experiments done measuring nucleation rates of essentially a pollutant. So we have nitric acid dihydrate and nitric acid trihydrate. Okay? And so several different experiments looking at the nucleation rates or the freezing rates of these droplets. So how quickly they freeze into the crystal as a function of temperature. And so if you measure the rate and then you do an analysis to extract out what that rate is based on nucleation occurring in the center, you get this set. And here we actually have a whole set of different experiments. So we have circles up here, we have diamonds, triangles in here, some squares, and some diamonds. They're all different experiments, okay, on the same system. If you reanalyze that same data and produce a surface and assume that the system nucleates on the surface, you get this type of phenomena. And so this is the same data, just analyzed differently. And so here we now have so much better agreement with a lot of the data falling down onto a more reasonable line. And again, you see this type of thing here. Most importantly, the thing to notice is there's a dramatic difference in rates. There's orders of magnitude in the rates you would predict based on volume nucleation occurring in the center compared to nucleation occurring on the surface of that nanoparticle. And so understanding where this occurs is an important idea. Okay, so with that kind of background, the type of questions that we want to ask is, first of all, what are the structures? We know there are icosahedra, decahedral, and FCC structures, but are there actually others? And of course, I wouldn't be putting that question up there if we hadn't found that there are other different structures. And so before you can study nucleation and formation, you need to know what it is you're actually forming. And so that will be a large part of this talk. Then there comes the questions of how are these different structures formed? And critically, one of the key things we're trying to understand is what is the reaction coordinate that we will need to describe the system? Because the global structures are very different, we can't just look at an n-size cluster definition so easily. So we'll ask how is that formed, and particularly with respect to non-crystalline structures, those icosahedra and those decahedral structures. And then what is the role of the surface in this process? We've had a look at gold, and I'll talk about some of that. In particular, there's this interesting problem. So we have gold, and I'm going to show that it freezes in the surface and nucleation occurs in the surface. Lennard-Jones clusters also freeze, but they freeze into the core. So they start in the core and then freeze on the outside. Yet they both form icosahedral structures. And so the question becomes, does that mean there's multiple mechanisms for the way icosahedra form if I start from the outside and freeze it inwards, or whether I start from the inside and freeze out? Or is there some better way of thinking about how these icosahedra form that are suitable for both these systems? Okay, and so hopefully that is what we're trying to kind of see as we go through this process. So it's just some background again. I'll just go through this real quickly because you'll see this many, many times. So obviously we're talking about nucleation, and if we think about it in the classical terms, we've got this growth of one by one addition into some embryo of the structure. And here we have our work, and we have our surface terms, and this is our free energy gain from converting the system into the more stable phase. Here we have our N of n. So this is like the equilibrium number of critically sized clusters. Okay? We have our work, and these two are related through a probability. And so if we want to do simulations on the system, there are two things we need to be able to do. We need to be able to recognize our crystallites, and we need to be able to determine this work from our simulation. So the way we've done this, at least in the initial work, is we need some embryo criteria. So we're just going to have some atom at the center, and we're going to define its neighbors based on the radius. And so we pick this radius essentially based on the G of R, so we get this first shell. then what we're going to ask is, are the local orders around these particles similar? So first of all, we take the spherical harmonic, so the Q6 essentially of the particle around here. That gives us our first term, whether this particle, how ordered it is. But then we ask a little bit more. We ask, is the order of that particle correlated with particles next to it? You can imagine a situation where you have crystallites that are slightly different and they're growing in different orientations. They are not necessarily going to be part of the same crystallite. And so when we take that, we take the dot product, and if this dot product, which we call Cij, is above some certain threshold, we give them a bond. Okay, so that says, so the blue bond is these guys are just locally correlated. They have a similar sort of order on each side. We get this threshold value by comparing the liquid compared to the solid phase of this system. Now, one of the challenges we hear again with small systems is you don't get such a neat separation of the phases. And again, this is a symptom of small systems. And so before, in one of the talks earlier, we talked about making a difference between liquid-like clusters and gas-like clusters. You saw the distributions are well separated, and you could easily pick a point in between. We see here that that's not so the case. We still have to make a choice, but we know we're going to be making some error. And this is something you just can't avoid in these small systems. And so we pick that threshold. Once we've got the order, then we then ask if you're surrounded by enough particles of the same type of order, then you are a solid particle. And then we just join solid-like particles that are neighbors to each other to form an embryo. So this is our sort of embryo criteria for looking at nucleation in the system.
How do you deal with this threshold number of bonds for particles near the
Right, so thanks, that's good. So what we do in the simulations is, because particles on the surface are going to have fewer neighbors, we just require 50%. And so that's the same in the bulk and the same in the surface. So 50% of the neighbors satisfying this criteria will do the trick. Okay. So yeah. So now we have our criteria. We know how to identify a cluster inside the system. We want to be able to work out the work of that. And so we have our n-sized equilibrium number. This n of n is really just the probability of finding one n-sized cluster plus the probability of finding two, finding three n-sized clusters, etc. The probability of observing a cluster, an n-sized cluster in the system, is just this, okay? So without these coefficients. So if we're sufficiently just under metastability, where the appearance of these clusters is relatively rare, then essentially what we say is this equilibrium number is essentially equal to this probability, which we know is we can get from the work of forming the fluctuation.
So what is your notation? What is little n?
Little n is the size of an embryo, and big N is, well, big N is the equilibrium number of this size n. This is the probability of seeing this size n. This is the probability of seeing one. This is the probability of seeing two of n-size clusters. And obviously, because we're taking the average, we have the coefficients in front. Okay. Then this is just the probability. And that's the probability of seeing. So this is the total probability of observing something in the system, is equal to the probability that there is one, plus the probability that there are two of them in there, plus the probability there are three, etc. And so when this becomes rare, this probability is small, as are these. These go out as well, and we can essentially say that these two things are approximately the same, and then we already have this equality on this side. And so under these conditions, when everything is rare, we know we can just measure the probability of appearance, and we'll get essentially the n of n and the work. Okay? So now we have the two ingredients. We can go ahead and measure this. Obviously, this is a condensed phase. We have many, many problems. So parallel umbrella sampling is one. We've got this low probability of appearance of the critical cluster. Remember, it's a rare fluctuation, so we need to bring that into being. So we have a simulation where, again, we just use the umbrella sampling, and we use the parabolic potential to make sure that we sample around this equilibrium, this size, and then we have around this size and around this size. But because we're dealing with these nanoparticles, this potential energy surface is very complicated. It's very difficult for these systems to rearrange. what we're also going to use is parallel tempering, so we're going to generate a larger ensemble with many, many different temperatures. And so now we do the simulation at multiple temperatures, multiple sizes, and then we just make tempering switches between these systems. Okay? So that is going to be a way we generate our statistics. And I'm sure you'll see a lot of that as we go through the school in particular. And so this is what we get. So we're looking at a gold nanoparticle of 456 atoms. Okay? This is the work. This is the size of the embryo. And we see the normal sort of size behavior as a function of temperature. So here we have high temperature. As the temperature comes down, we're becoming more and more deeply supercooled. We see the critical size and the height of the barrier coming down, but we also see some unusual behavior, particularly at very small sizes. And in fact, it looks as if this is actually growing rather than coming down in the normal sort of picture of nucleation that we see. So one of the things we want to understand is what is going on with these very small sizes, and can we come up with some sort of phenomenological type model that describes this nucleation process. And so the first thing we can include immediately is core nucleation. And so if we take the work, we have a sort of phenomenological model based like this, where we have a crystallite in the center, and it's totally surrounded by the liquid phase, and this is our data, and this is the best fit you can get. And so obviously we can immediately write that guy off. Not too surprising if we go and look into the system and ask, where are these nuclei forming? And so the way we've asked this question is we ask, how many particles so this is the size of the largest cluster inside our system. This is the number of particles inside this cluster that are on the surface of the whole nanoparticle. Okay? So the fact that we find some tells you that at all times, or at least most of the time, there is some part of this embryo excuse me, that is in contact with the surface. And so what we see in particular is two slopes to this. Essentially, the slope of this gives you the fraction of particles in your embryo that is in the surface. And so for very small particles, we see about 60%. So about 60% of the atoms inside the embryo appear at the surface, and this drops to about 40% once you get above this certain size. So this is kind of suggesting that there's some change in the shape of the particle as this is going on. And in fact, we've gone on and measured, or started to measure the surface areas and shapes of these things, and that's exactly what we see. For very small clusters, we see a different shape compared to very large clusters. And so that is one of the things that we're noticing as we go through. So we can come up with phenomenological models for the surface. Here we have just a sort of spherical cat model. So this is the liquid phase, this is our solid phase, and we have some nice easy parameters. We can convert this into n. Okay? And so what do we have if we look at the work? We just have our chemical potential term. Now remember, we've got different surface areas. So we've got the liquid vapor interface, we've got the solid liquid interface, and we've got the solid vapor interface. And they're contributing to this process. And in fact, there's a slight error because one of these will be negative. This guy should be a negative term, right? Because this guy, I'm losing surface as this guy grows. Okay? And so then we try and fit this data. And what we've got at the end here, excuse me, my voice is disappearing, is tau, which is a line tension associated with, I've actually got some water here. Whoops. Yep. A line contact where we have the particle or the three-phase contact line associated with this line here. If you try different models and you leave this line tension off, you get improved fits as you look for different variations you can have here. The best fit we get is when we include this line tension. That's not too surprising. The line tension itself, remember this goes as 1 over r, so it's going to have a big effect in the small sizes. Okay? So that's important. However, it turns out, despite the fact that we get a really good fit, none of this makes sense because the parameters you get out of this suggests that one of these surface tensions would have to be negative. Okay, no matter what sort of scenario we use, we can't avoid one of the surface tensions becoming negative. And so that obviously doesn't make sense. You can't have a negative surface tension. So we've looked at one slight variation, and so we can also calculate the free energy not just as a function of the size of this particle, we can work out where it is, and so this is the location of the center of mass of that embryo cluster that is growing. And as we can see again, it's occurring at the surface. And if we introduce a sort of, again, a very simple model just to get an idea of what's going on, we just take a sphere growing inside a sphere that can occur at any radius out here. If we don't include the line tension, we get this type of model, which again fits most of the data except at very small sizes. And then if we include the line tension itself, we get at least a better shape. I wouldn't say anything about the detail of the numbers that we get out, although we're getting reasonably close to the surface tensions seen experimentally. But the key point is now we're getting most of the general behavior when we include the line tension associated with this surface. So that is one of the stories. So for this gold system, we're nucleating at the surface. However, one question that comes up now is, especially in the context of this competitive nucleation, what structure is it that we're actually forming? Okay, so the order parameter we used was based on Q6. So that is the Q6 spherical harmonics. That picks out FCC very, very well. And so what we anticipate is this is going to be nucleation to the FCC type structures. But what we want to know is, can we get a little bit further? And so now we're going to get on to more detailed analysis of, can we just get a better description of the particles inside these embryos? To do that, we need to identify the environment around an atom or the environment of an atom much more carefully. Before we were just using this Q6, but now what we're going to use is common neighbor analysis. Essentially what that tells us is, based on the relationships of the various neighbors of our atom I, what is the nature of this guy in the middle, and we can work out whether it has icosahedral type symmetries or whether it has FCC or HCP. So that's going to help us get a lot more detail. The second feature we're going to use, or second technique we're going to add into our description, is we're going to use some what might be called inherent structure quenches. So this is the potential energy surface of this cluster as it moves around. And so what we can do is take one configuration, once we get it frozen, we can do a conjugate gradient quench to its minimum, and then have a look at the structure analysis at that point, and we'll get a much clearer picture of what is going on. And so just so that you probably can't see the buttons or the points, I'll come back to this in a much clearer picture. The idea here is, if we have a look at the structure as a function of some order parameters, this is just the number of icosahedral atoms, this is the number of FCC, and this is just the surface. Without any quenching, you get quite a broad scope of structures, but when you have a look at the same quantities after doing the inherent quench, what you see is they start to group together. And that's giving us an indication that really there are some common structures that we're seeing inside the system. And so the key idea now is, can we work out what these type of structures are? And so again, I just want to stress that now we're looking at a Lennard-Jones particle. It's going to be 600 atoms. And we started off in this work to try and understand, again, the surface versus bulk. So we've measured Q surface, which is just Q6 for the surface atoms, and here is Q bulk of the atoms inside the core. Okay, and so again we use parallel tempering in this dimension and this dimension and in temperature, and we use bias simulations as well. So this is a free energy surface results from a parallel simulation of about 200 processes at a time. And so this is the temperature just above the freezing temperature of this liquid. And here we have the minimum associated with the liquid phase. And here we start to see a free energy minima growing in. As we decrease in temperature and go through the transition, this guy starts to become more prominent. And most importantly to note that this is ordered in the core, no evidence of any ordering in the surface. And that's what I said before, is we know, in a sense, that Lennard-Jones particles prefer to freeze inside rather than at the surface, which is different from the gold. We go to a lower temperature, we start to see some deformation of this liquid phase, a new minimum is growing in here, and eventually at the lowest temperature we worried about, we have a minimum here, a minimum in the center, and we have some sort of remnants of the liquid phase. To have a look at what these structures are inside these, what we did was essentially take structures from these minima and quench them down to their inherent structures. And so in terms of these Q parameters, what we get is we just get some core ordering of these guys. These guys order in the core a little bit better. These guys here order on the surface significantly better. And then if we take things from here, which was, remember, with the liquid, then we kind of get a scattering all over the place. And so now we want to try and understand, by looking at the common neighbor analysis, what these structures are. And so our first guess when we saw this was, well, these are just our icosahedral structures that we know about. Turns out not to be the case. If we have a look at the liquid phase, so these guys quenched from here, I've highlighted in brown and made them large all the icosahedral atoms in the bulk. As you can see, they're sort of essentially randomly distributed. Turns out that they're sort of sitting just below the surface, and that's sort of frustrating any possible order inside the system. So that's what you kind of expect from a liquid type structure. Okay, lots of icosahedral order inside, but it's sort of randomly distributed. If we look at this guy, rather than seeing an icosahedral structure, what we see in fact is this massive tetrahedra sitting inside the center. And so if you count along these edges, what we're actually seeing here is a tetrahedra of length edge 7. That is the tetrahedra size that would make up a 951, or I think it is, I can't remember the exact number, perfect icosahedra. 20 of these would make up a larger icosahedra. But because it's too large, it obviously can't grow. Okay, it's so this is the structure that we see. And we see these at intermediate temperatures. You can kind of imagine why we see this. We got good ordering in the center with FCC, but we've got a nice disordered surface, so we're getting some stabilization, a little bit from the better energy of packing in the center compared to an icosahedra. And then here we have the surface entropy, which you don't have for the icosahedral state. If we have a look at what these guys look at, now we don't just see one. Here is a single tetrahedra. And remember, a key element, this is a free energy minimum. So this is essentially like a phase, as much as you can have a phase in a finite size system. Here what we're seeing is now multiple tetrahedra forming inside the system, and these are the right size. So these are size 6. Okay, so these would potentially form the icosahedra that fits inside this 600 atom system. But now we're seeing multiple of them. And so now one of the things we want to try and understand is, well, what is the nature of these phases? Do they appear in terms of the nucleation? Because if you want to understand the nucleation process, you want to know what happens as the liquid freezes. So here we have equilibrium liquid. We at T equals 0.53. Then we just take an instantaneous quench down to 0.44. And so now this is going to be an important point. I should go back one picture. Now this is an indication of how important reaction coordinates and understanding reaction coordinates are. So key thing is here, these are global order parameters. This is all of the surface atoms. This is all of the bulk atoms. So it's not describing the nucleation process. What it's giving us is information about the nature of the phases. And so you can see that if I start out on a liquid phase, there's no way I go all the way through this phase minima to this one in a nucleation process to get to here. That's telling me that this reaction coordinate is not right. Also what we see is the barriers that we have here are relatively low. These are in order of KT, 0.5 KT. So this barrier between these structures, and if we look back one with regard to the liquid to this guy, 4 or 5 KT at most. When we do the freezing experiments, we have to go to much lower temperatures than we did our free energy calculations in order to see freezing at all. What that tells you is that the nucleation process is seeing a much, much higher barrier than we see from our free energy calculations. But again, that's because the free energy calculations are related to the phase behavior rather than the reaction coordinate that actually describes the nucleation process. And so that's one of the things we want to try and extract. What is that correct reaction coordinate for these different structures? And so when we do this and then we crunch the inherent structures down, what we see is a beautiful picture like this. This is our Q surface, this is our Q bulk, and what we're getting is nice groupings together of these different structures. This is just our L, so this is L5 now. So now this is actually forming groups of clusters or tetrahedra that are smaller than required. So this is now L equals 5, so these would actually form a 309 sized icosahedra. Here at this point, there's 8 of these tetrahedra completed, and the other ones are almost starting to complete, and so we're getting close to forming the complete icosahedra. And then if we just go through these, this is the 6, the same one we see essentially before in our free energy calculations, we're seeing inside our molecular dynamics. What is that telling you? That tells you that the free energy surfaces are important with respect to our nucleation process. These guys are ending up inside those free energy minima. For L equals 7, we see the large tetrahedra that we saw before, but we also see this additional structure. Now this is essentially a decahedral structure. If you look down, there's a line going through the center of our particle of the icosahedra, bulk atoms, and then we have these side guys coming off the side. And then we even have an L equals 8 in our molecular dynamics. So now this is way too big to form. And so now we just get the single line. What we have is, that gives us this branch here. And so the key element that combines all of these guys is there is this three-dimensional arrangement of these icosahedral atoms in the core, okay, for different sort of tetrahedra that are forming. Along this core, essentially we only see, down here we see these one-dimensional icosahedra. So this is the pure decahedral structure. Now I've colored in red the HCP packings and see the nice 5 structure, layers coming out. And then this one has 0. So as we move along here, you have some icosahedral atoms, but they're just linear. There's no three-dimensional structure. Eventually you lose that, and you just have the FCC structures left. How can we rationalize this type of relationship? So this is, remember, this is Q ordering on the surface. This is Q ordering in the bulk in terms of those icosahedra. It turns out that we've looked at all the different types of atom types. The only ones that correlate with these pictures is the number of bulk icosahedral atoms inside the core. And so if we just look at the bulk order, what we see is just a linear relationship as the number of icosahedral atoms increases. That makes total sense. This is an FCC order parameter, they're picking out the FCC. These guys frustrate that order. They're 5-fold symmetry rather than 6-fold. So that is getting this decrease, and this is just this positive branch, and the red ones are this negative branch. But what surprised us was the fact that these N bulk icosahedra also tell us what is happening in the surface, even though these guys aren't in the surface. Okay, so again, we get this decrease associated with this, and then what we have is an increase of QS, which is the same as we get here. And so we don't really understand why this is so, but what we expect, remember, with the increasing number of icosahedra, bulk icosahedral atoms, we're getting more and more of these tetrahedra formed. And so our suspicion is that they're forming as a template to order the surface as more and more of those form, and that's leading to this surface ordering. What we want to have a look at is the trajectories in terms of these order parameters. And so now what I've got is just the number of bulk icosahedral atoms along this axis. We've got the number of FCC atoms inside our system along this axis, and then we just have our Q surface. And this is a trajectory that ended in an FCC structure. And so we start out at early times, it's bouncing around, and so this is the liquid, so low FCC, low icosahedra. And then once it nucleates, it shoots across and forms a nice FCC structure. If we compare that to one that formed a large number of icosahedra, so this is now icosahedral structure, again, it bounces around in the liquid to start with. The nice thing about this is we see this sort of fluctuation phenomena of nucleation. So it actually explores part of the pathway down here, then bounces back, and then it kind of explores out here and bounces back, and then it finally decides to go over and freeze into this system that contained multiple tetrahedra. This is just now, and this is going to spin around, so you can see it more clearly. So this is, again, our FCC structure that we just saw before. This is one of those decahedral structures where you get a lot of FCC, but you have a line of decahedral structures, so they go along a similar sort of line. But the L equals 7 tetrahedral, so this is the structure where you have the core filled up with FCC, but surrounded. And so as you can see, this follows a very distinct path down into this region, and the nucleation paths are very different from here. So now that we can start to identify all these different structures, our goal really is to look back and try and now follow these trajectories and understand what is it that distinguishes the formation of this guy from these guys in the kinetic sense. And so that's kind of where we're going. If we have a look at gold, some work has been done earlier, they actually see similar structures. So they saw for different size systems. Now they didn't do any nucleation studies, they just cooled these guys down and saw these structures form. The key difference now is that we find these tetrahedra, but what you've got to do is look into the surface. One face of these tetrahedra now like to form in the surface, whereas before with the Lennard-Jones system, what we saw was the system just likes to form the tetrahedra below the surface. And so what we're seeing is the same sort of features that we see in Lennard-Jones in gold clusters. And so if you do the same sort of analysis, you see something that's actually quite similar. It looks a little bit different. So this is Q surface, Q bulk still. This is just the liquid clusters. And so we put those on because what we're trying to do is be able to differentiate between liquid and the different structures. So if you ignore those, then essentially you still see this tick mark that we saw earlier. And again, so these are the icosahedral. So that's the liquid again. For these liquid structures, you just see sort of clusters of these icosahedral atoms, but not arranged in any order. For these guys, you see now we're ordering our tetrahedra, and so there's multiple tetrahedras of the right size. This is an interesting case. This is the 459 structure. This is halfway between two different magic numbers. And so what we actually see in here is clusters that form half of one size and half of the other size. And so here, in fact, this is the L equals 1, 2, 3, 4, 5, 6. And then on the other side, you can start to see an L equals 5 tetrahedra forming on this side. And so that's just a function of the size that we chose. And then for larger sizes, again, we see the decahedral structures and these guys. So what does all this mean? So one of the key things is we're starting to see new phases. The fact that the icosahedral, decahedral structures and the FCC structures are not the only structures available to these nanoparticles. There are a whole set of intermediate temperature structures that we see based on these tetrahedra, and in particular this large tetrahedra that's forming in the center. And so one of the things that gives us is a clue to how these icosahedral structures are formed in a general way. Remember what I told you was at the beginning we have these icosahedra are made of 20 tetrahedra. Gold particles freeze from the surface, Lennard-Jones particles freeze from the core. But if we just think about the tetrahedra, then maybe the way we can think about building this complex structure is by first making tetrahedra and then arranging those tetrahedra. And now that sort of picture, you don't have to worry about surface nucleation and core nucleation for different mechanisms. It's just one sort of mechanism for these icosahedral atom formation based on these tetrahedra. And then we're just looking at the different reaction coordinates, and we're going to try and back out the nucleation barriers associated to these different structures now that we can actually recognize them. And so then just the final acknowledgments, the students again, and the funding. So here we go.
Quenching here.
Oh, sorry.
Yeah. You saw the places like A, B, C. Those are preferred sites for nucleations. Those are random, or you have some defined conditions?
These guys?
Yes.
Well, what we how we chose these?
Yeah.
Oh, at the moment, right? Yeah, we haven't got any criteria for saying, well, the boundary of this should be here, right? What we've done is we've looked at these structures and picked them out and had a look at them, right? But essentially, what we've been doing is hopefully these order parameters are going to start to tell us about that. So we look at all these structures and we look at all their different FCC type atoms, icosahedral atoms, etc., and we see that these are generally forming liquids. But yes, we don't have a sort of, well, yeah, we don't have a detailed analysis of being able to determine what that is. Yeah.
Thank you.
Almost a philosophical question. You have so much information here from the simulations. Are you able to comment based on this on how large a cluster has to be in order for the idea of a surface energy to make sense?
That's a very good question. So certainly with respect to like surface tension, right? How would we define a surface tension? I would say it's very difficult. I mean, we've used phenomenological models to look at that, and really the thought there is that we get a basic idea of the physics. How you would define a surface tension becomes very difficult. If you've only got 3, 4, 5, 10 atoms in a surface, can you really define that surface tension? And it's going to vary on size and shape. But still, a surface energy, in a sense, must be there, but just not in its bulk form, right? I mean, there's still atoms have different environments compared to, at the interface compared to when they're in the core, compared to when they're in the surface, down to a certain size.
But in principle, maybe you could be more quantitative than this.
Right, well, we would like to be, yes. One of the things we're sort of looking at is, can we look into the cluster and divide up the space of each atom and define and find surfaces between the different ones at an atomic level. And that's going to help us hopefully, yeah. Once we can find those atoms, then maybe we can calculate surface energies associated with those atoms at those interfaces. But you've still got to come up with some definition of what you say is at the surface. That's one of the challenges, right?
Maybe you don't.
Or maybe you can't, right? Maybe you can't, that is true. But certainly we want to try and do that because that's kind of what we know at the moment.
Okay, any other question, comment? Well, one thing that I was wondering about is whether it makes any sense to talk about supercooled liquid in this kind of small systems.
Right. Well, I think it's reasonable on some level, in the sense that maybe I can't find it. We can find a region where there is the freezing transition. So we can certainly find that. And then when we do a molecular dynamics simulation, if you quench and you don't quench too far, then you get a region or a time where the system comes to equilibrium with respect to its energy for a significant period of time before it then freezes. And then this freezing happens at random times. So that would at least suggest that there's metastable. But you can't go too far. And in fact, we've done other calculations where you look at the probability of the largest cluster, similar to what was done this morning, and we see the barrier disappear for that at a certain temperature. After that, nucleation happens so fast, or growth happens so fast that, yes, you lose the stability of the liquid.